Hi, in this chapter we are going to talk about ternary search trees, so let's get started. With the help of tries, we can search and sort strings very efficiently. So that's why trie data structures came to be. Why is it good? It's like a tree-like structure, but with the help of this trie data structure, we can sort strings efficiently, not just integers and not custom objects. It's specified to strings. And the problem is that these tries consumes a lot of memory. So we should use this ternary search tree data structure instead, which we are going to talk about, which stores less references and null objects. Just to show, this is a typical trie data structure. This is not a ternary search tree. All of the edges represents a character, and it has a tree-like structure. And it serves as a hash map. So we have words, these are the keys, and we have integers, for example, or values we want to store. And if you see that on the second level, on the first level there are just single characters, the second level there are words with 2 characters, on the third level there are words with 3 characters, so we just have to adjust the given character represented by a given edge if we go deeper and deeper in this tree. The ternary search tree is something different. So this is a trie data structure. And ternary search trees stores characters or strings in nodes and not keys. So it doesn't have these edges represented by characters. And in a ternary search tree, each node has 3 children, a less, an equal, and a greater. So can we balance these ternary search trees with rotations as we have seen with binary search trees and AVL trees? Yes, we can, but it's usually not worth the trouble. It's very hard to implement and it doesn't matter. It can be used instead of hash maps. It is as efficient as hashing, because hashing needs to examine the entire string key and the TST does not. And that's why it is much more efficient, because if we have a key, for example, that's very large, then hashing is going to have to examine all the characters in the key, but a ternary search tree doesn't. So as we discussed, this is the trie data structure. This is not the ternary search tree. The ternary search tree supports sorting operation. It's very important because hash maps do not. So TST is better than hashing, especially for search misses when we try to find something in our data structures that are not present. And it's flexible, it's more flexible than binary search tree. So usually there is no perfect hash function, and collision may occur, and that's why the constant time complexity of hash maps are usually not true. So the conclusion is that the ternary search tree is faster than hash map and more flexible than binary search tree. So there are lots of applications. It's very important in package routing. The router directs the packages in the direction of the longest prefix, and it can be found very quickly with the help of ternary search trees. For example, there are other applications such as prefix matching or Google search. You try typing out a word or a given phrase you are looking for, and Google try to guess that what you are going to type in. So this is the prefix matching in the Google search. We can use that for search instead usually, but with the help of this ternary search tree data structure, we can solve all of these problems very efficiently. So how it works in practice? We have a put and we have a get method, as we have seen in the hash maps, because it's like a hash map. We want to store key value pairs. So if we want to put, for example, the key cat and the value 23, in other words, we want to put the 23 with the key cat, we keep constructing a ternary search tree. And we keep constructing according the keys, so the cat words, because in the ternary search tree we are going to represent each of the characters in the key with a certain node. So we keep constructing. We start with the first character, which is the C, and we come to the conclusion that the C and then the A and then the T. So in the first key in our while constructing our ternary search tree is quite easy. It is straightforward. We just have to build up a structure like this. Then we are going to insert 23, of course, and the t character is going to be assigned a value 23. Then we want to insert the apple, and here we have to make sure that we keep comparing the nodes of our ternary search trees with the characters of our keys. So we have the key apple, and we start at the beginning, of course. So the leftmost character is A, and we come to the conclusion that the root node is C, and the A is smaller than the C in the alphabetical order, and that's why it is going to be the left child of the C. As we have discussed, the ternary search tree can have 3 children. Each of the nodes can have 3 children. A left child, which is smaller, an equal child, which is the middle, and a right child, which is the greater character representation. And then the P is, of course, we keep constructing our ternary search tree like this. Then we insert the value, of course. Then we want to insert the car. We keep comparing the first character, it is the C. We come to the conclusion that it is equal because the first letter in the car key is C and the root node is C. And if it's equal, we keep going into the middle direction, on the middle branch. So we keep to the next one. The second character in our key is the A, and it is a match again, so we keep going. But here we come to the conclusion that the third character in our key is R, and it is a T, and T is greater than R, the R is less than the T, so we keep going to the left side. So it is going to be the left child, it's going to be the left child of T. And we insert the 6. Then we want to put the caret, we want to insert the caret. We want to insert the number 68 with the key caret. So we keep constructing our ternary search tree and have to make sure that we're checking the first element from left to right in our key with the root nodes and so on in our ternary search tree. So the first character is a match because the root node is C and the first character in our key is the C. So we keep going on the middle branch. Then A, it is a match. We keep going. Then the R is smaller than this T1, so we keep going to the left. It is a match. So we keep going on the middle direction. It is an R, and then O and T. It's pretty straightforward. Okay, and we insert the 68. Then we want to insert the cow, for example. Or, to put it in other words, we want to insert the 112 with the key cow. The C is a match, so we keep going on the middle branch. But the A is not a match. The O is greater than A in the alphabetical order, so we keep going to the right direction. This is the O. And then we insert on the middle node the W. And we insert the 112. So we keep constructing a ternary search tree like this. And if you may recall, it is totally different than a trie, because in a trie we keep from layer to layer, and on each layer there are a given word with one more character than the previous one. So if we may recall, for example, it's very important to be able to make sure that you understand the difference between a ternary search tree like this. Here in a ternary search tree, each of the node represents a character. In a trie, not always. We have nodes in a trie that represents a given word. The root node has no character. The first layer contains one single character. The second layer contains 2 characters, and so on. We keep building our trie like this. And this trie data structure is not efficient. So, yes. And what about getting? We have seen in the hash maps that we want to put items in our data structure, and sometimes we want to retrieve values from our data structure with the help of the keys, of course. So we have this constructed ternary search tree, and we want to get the value associated with the key car. we keep checking whether it's a match, and the root of the ternary search tree is a C. The first character in our key is the car, so we keep going on the middle child. A, it is a match again, so we keep going, and T is a mismatch. The character we are looking for is R, and R is less than T, so we keep going to the left. And we come to the conclusion that we have examined the whole length of our key, so it is a match. We have the car key, and there's a value 6 right next to the R, so we return with it. And that's how this getting mechanism works with the help of ternary search trees. If we would looking for example, the cow, we just check whether the first character it is a match, the second character is not a match, we have to go to the right, it is a O, then a W, and we return with 112. And why is it good? If you consider it, it's very efficient because we just have to consider if it's a mismatch, for example, so we are looking for airplanes. We came to the conclusion on the second characters that is going to be a mismatch. Our ternary search tree data structure doesn't have any value associated with the key airplanes. And unlike this data structure, for example, hash map, with the hash function, we have to examine the whole key. So this is why it's very important to be able to construct a ternary search tree, and this is why it is much more better than constructing a trie. So some important notes that we should combine the airway tries with TST. The airway tries it means that the trie has, each node in the trie has as many child as the R. So for example, the R is usually 26, the number of characters in the English alphabet, for example. So we should combine the two, the TST and the trie. At the root, it is an R-way trie with many children, and at lower levels it becomes a TST with 3 children only. Because that is one of the most important differences between a ternary search tree and a trie. The tries can have as many child as we want, but a ternary search tree has to be 3 children, a left, a middle, and a right. I mean, not always. It can be a null pointer, of course, but it can have at most 3 children. So this combination is quite efficient, so we can make use of the tries and the TSTs, of course. So let me tell a few words about the difference between ternary search tree and hashing. The hashing needs to examine the entire key, because that's the way the hash function works. We keep constructing our hash values according to the hash function, and the hash function is going to examine the entire key. This is the basic concept of hash maps. So search hits and misses cause the same in a hash map. The running time and performance relies heavily on the hash function, and it's not very good if we rely heavily on the hash function, because in practice these hash functions we are not able to construct it perfectly. So it doesn't support as much operation as a ternary search tree, for example, sorting. On the other hand, the ternary search tree works only for strings. This is the main disadvantage for ternary search trees. It only examines just enough key characters, and that's why it's much more efficient than hashing. Search misses may only involve a few characters, that's why it's only examined just enough key characters. It supports more operations, such as sorting, for example. And it's faster than hashing, for misses especially. When we want to try to find a key, for example, in a ternary search tree that doesn't exist, we can find it that it doesn't exist very quickly. And of course, it's much more flexible than the binary search tree. So this ternary search tree is a very good data structure. The main disadvantage that it only works for strings. And of course, it has some applications, so it can be used to implement the autocomplete feature very efficiently. For example, if you have smartphones, you want to find something on Facebook, you are searching for something on Google, it is going to have an autocomplete feature, and it can be solved very easily with the help of these ternary search trees. Or can be used for spell checkers, near neighbor searching, which is spell checker is a special case, of course. And for databases, especially when indexing by several known key fields is desirable. So it's I think it's very important data structures, and there's lots of applications. So that's all about ternary search trees. Thanks for watching.